Hello, everybody. Welcome to the GeoAI Speaker Series. I'm Micah Brockman. I'm the Community Manager here at the Open Geospatial Consortium. Really a pleasure to have everyone here with us today. I just want to do a really quick microphone check. Can folks online hear me okay? Does the audio sound okay? You can go ahead and type in the chat, or you can type into the question panel as well. Excellent. I'm seeing a confirmation both in the chat and the question panel. That is fantastic. Glad the audio is working just fine. So our format for today for the GeoAI Speaker Series is we're going to have a 30-minute presentation followed by a question and answer session. And you should all see that question box, which I can see many of you are already using. That's fantastic. That's the way to type in your questions for the speaker, or if you have any questions for OGC staff, you can type those into this question box as well. If it's a question for OGC staff, we'll try and answer it as soon as we possibly can. If it's a question for the speaker, we're going to take those at the end in the order that they were received. We are recording this session, and we will make this recording available after the webinar is over. We're going to post it on our OGC YouTube channel and also put it on the public landing page of the OGC Artificial Intelligence for Geomatics Working Group page. So I'm going to go ahead without further ado and turn it over to Lokendra Kachwan. He's the co-chair of the OGC Artificial Intelligence for Geomatics Working Group, and he is going to introduce today's speaker. So Lokendra, please take it away.
Thank you, Micah. So hi everyone, welcome here for our first or inaugural talk for the GeoAI series. On behalf of the GeoAI Domain Working Group, I'm really glad that we could get it started. We have been working on this, getting started this GeoAI talk series for I think past 5-6 months. So so this is really great that we now have our the series getting started with, and the first speaker is, I would say, like, he's an inspiration for a lot of folks here, at least for me, and I know that a lot of people would have studied have been following his work or studied through books he's written and all. So I'll just give an introduction for Professor Vipin Kumar, who's our first our inaugural speaker for the GeoAI talk series by the Geospatial AI Domain Working Group. Professor Vipin Kumar is a Regents Professor and holds William Norris Chair in the Department of Computer Science and Engineering at the University of Minnesota. His research spans data mining, high-performance computing, and their applications in climate ecosystems and healthcare. He also served as a director for Army High Performance Computing Research Center from 1998 to 2005. He has authored over 400 research articles and co-authored 11 books, including 2 widely used textbooks, which probably a lot of us might have used, like Introduction to Parallel Computing and Introduction to Data Mining. And there's a more recent one, edited collection. It's called Knowledge Guided Machine Learning, and I would recommend everyone to probably go through that for sure. His current major research focus is on knowledge-guided machine learning and its applications to understand the impact of human-induced changes on the Earth and its environment, broadly in the climate domain. And that's a very big topic in area of interest for all of us here in geospatial domains. That's why we have him here. Kumar's research on this topic is funded by National Science Foundation's AI Institutes, Big Data, Infuse, STC, GCR, and HDR programs, as well as ARPA-E, DARPA, and USGS. He has recently finished serving as the lead PI for a 5-year $10 million project on understanding climate change and data-driven approach. It was funded by NSF Expeditions in Computing Program. Professor Kumar is a fellow of AAAI, ACM, IEEE, AAAS, and SIAM. His foundational research in data mining and high-performance computing has been honored by ACM's SIG-KDD 2012 Innovation Award, which is the highest award for technical excellence in the field of knowledge discovery and data mining. In 2016, IEEE Computer Society Sydney Funback Award was also awarded to him. That's another so that's IEEE Computer Society's highest awards in high performance computing, and he's also gotten the Test of Time award from 2021 Supercomputing Conference. His work on knowledge guided machine learning is important because these techniques are fundamentally more powerful than standard machine learning approaches. They are particularly relevant for scientific and engineering problems that we all work on in the geospatial domain, like climate change, loss of biodiversity, food, water, energy security, nexus. So these are, especially they relate to the growing population of the world, are some of the greatest environmental challenges that we are facing as humanity. And these problems are inherently location-based, geospatial in nature. And his talk would be addressing these challenges. It would give an overview of the new generation of machine learning algorithms he's been working on, where scientific knowledge is deeply integrated in the design and training of machine learning models to accelerate scientific discovery. Without further ado, I would ask Vipin to take over and get started. Thank you so much, Vipin, for agreeing to come give this talk.
Thank you, Lokendra. Can everyone hear me? And can you see my slides?
Yes, we can.
Perfect. Thank you.
Fine. We can see your first slide.
That's right. That's good. Yeah, that's a great start. So thank you. Again, this talk, as Lokendra said, is about what machine learning could do, especially a new generation of machine learning, which is guided by scientific knowledge, can do for addressing some of the global challenges we face in the environmental domain. So just a very quick review of what these challenges are. Everybody knows about climate change. It's speeding up. Some hottest last 15 years have been all in the 15 years. You're seeing increasing amount of forest fires, frequency of droughts, increased frequency of floods, and even intensifying hurricanes. But changing climate is only one of the many challenges that we are facing, and there are a whole bunch of challenges that are interconnected in the sense that to solve one, you have to figure out how do you solve the other one and simultaneously. So the second challenge, of course, is how do we feed the world without destroying the planet? And to be more specific, just want to remind everybody that in year 2000, we were 6 billion people on the earth. And last year, we crossed 8 billion people. So you see a 33% increase in the population in a very short window of time. And then the question is, how do you feed so many more people? You have to grow more food. And how do you grow more food? One of the different ways of doing it is to convert more of the forest into agricultural land, which is what we have been doing for since we started agriculture 10,000 years ago as a humanity. Now, when we are sort of trying to do that with this major increase in population, we are putting stresses on the tropical forests. And I'm showing you in this picture on the top right. The picture is from Indonesia. You see the right side is dense green forest, and on the left side of this picture is the forest cleared for oil palm plantations. And basically more and more of this is happening in different parts of the world. If you go to the Amazon, you will see forests being cleared for sugarcane plantation, soybean plantations, and so forth. And as you clear these forests, you have direct impact on the biodiversity, and biodiversity, even if you solve the climate change problem, is a huge problem by itself, in the sense that the entire web of life depends upon the diversity of life that that supports us, as human beings. Now, in addition to these two challenges, climate change and biodiversity, the other one that is perhaps even more urgent and immediate is the stresses on water supply. Fresh water is absolutely critical for life, and its supply is coming in under stress, both because of increasing population, increased water use, and changing climate. And as they say, some of the worst impact of climate change would be manifested into the society through water. And that means the availability of water is becoming less and less certain, even though there may be droughts in some places and floods in some places, but it's just the certainty of availability of water is sort of decreasing. And the last challenge, which is of course manifests at multiple scales, is the quality of water that is impacted, of course, by agriculture, which of course is intensified using nutrients, using fertilizers. In case you're trying to sort of reduce the impact on the forest, you try to improve the productivity of the land, and that means you use more fertilizer, and then much of that gets washed into the water and goes into the lakes and the rivers and the oceans, and of course that makes the local on a local scale, it makes the water to be undrinkable. It increases cost of processing this water, cleaning of the water, and in the longer term, it nitrifies the oceans, and if the oceans nitrify, the ocean life dies, and the oceans sort of become dead, then the rest of the planet life cannot survive. So all of these, as you can sort of see, are interconnected challenges that we are facing, and there are a whole bunch of issues that people are trying to understand. And for example, we are trying to understand the impact of changing climate and human actions on the global water cycle and the aquatic systems. We are trying to figure out, are there management strategies that we can design that will reduce the carbon footprint of the agriculture while improving the water quality and perhaps reducing the need on water and so forth. So there are all these questions, and big increasingly, this talk is about how could machine learning, and especially this new brand of knowledge-guided machine learning, could help address these challenges. Now, there has been interest in using harnessing the data revolution for scientific discovery, not just today, but for many years. And as you can sort of see, this data revolution has been sort of unfolding over last many decades. I would sort of say at least 5 or 6 decades, and it's happening because of the confluence of three different developments. One of them is increasing amount of data, and again, this group, OGC, of course, is all about creating more and more spatial data. The second component is increasing amount of computing, and the third is the more and more powerful algorithms that are becoming available and that have revolutionized all aspects of our life. And increasingly, there is an interest in scientific community to leverage these. Already over the last several decades, people are beginning to apply these machine learning algorithms to the scientific problem. And there have been many successes, but also many disappointments. And many of the disappointments have been because of the limitations of the standard black box machine learning algorithms when they're used in the domain of scientific discovery. And some of the limitations are that these black box ML algorithms require a lot of data to be successful. These are very complex models, and they require a lot of data for training. And they can also generate physically inconsistent results because they are not aware of the scientific laws that underlie the nature. Oftentimes, they're unable to generalize to scenarios that are unseen, which is a huge problem, and it's a especially difficult problem in the context of geospatial domain, because the relationship that exists in one region on one time do not often hold in a different region or different time. So which means you need methods to be able to generalize, and this is a huge limitation of the machine learning. And as a result, there have been many high-profile failures of applying standard machine learning algorithm into the scientific domain. So what we have is two different paradigms. One of them is pure standard theory-based models that are built using scientific paradigm. But these methods, as we will see later on, are bound to be approximate versions of the reality, and they often have lots of parameters, and as a result, they have inherent biases. And then there are data science models that have been extremely successful in many domains, but they inherently require a lot of data. So you have two different paradigms. One of them uses a lot of scientific theory, but isn't able to make use of data as effectively. And there are data science models that are eminently useful in domains where there is a lot of data, but they are incapable of making use of the scientific knowledge. So this new paradigm of knowledge-guided machine learning, it tries to address the limitation of each of these paradigms by combining the power of state-of-the-art machine learning along with the knowledge that is inherent and embedded into it the knowledge that is inherent in the traditional scientific paradigm. Okay, for example, the scientific applications are governed by laws of nature, such as conservation of energy, law, mass and momentum, and there are other patterns, other consistencies that you can sort of be aware of from the domain. And this paradigm is about bringing them into this machine learning framework. Oftentimes, this paradigm is also called physics-guided, physics-informed, physics-aware, and more broadly, you can sort of interpret scientific knowledge to be more general version of this, because scientific knowledge comes in many shapes and forms. And it's a growing community. The KGML is a growing community. There are huge number of workshops, symposiums. We presented a series of these at the AAAI conference, which is the main AI conference over the last 4 years, including a very successful Bridge to AI program that we held in Vancouver just a few months ago. There are different workshops at the interface of machine learning and physical sciences. There's a book that we published recently, Look in Dimension, and there are programs and other reports that are coming in from different agencies. This slide is simply supposed to sort of summarize some of the challenges that machine learning faces in the context of scientific problems, the data sparsity, heterogeneity in space and time, the need to be able to model complex processes that underlie these ecosystem phenomena, and so forth. And then on the right side, I'm mentioning all of the different ways the traditional machine learning paradigm can be expanded to incorporate scientific knowledge. For example, by modifying the loss function to make it more aware of the physical laws, being able to initialize these machine learning algorithms, models, using imperfect physical models, or designing the machine learning architecture that are cognizant of the underlying structure of the processes and how they interact. And in some cases, even building hybrid models in which there are components that are pure machine learning based or KGML based, or the other components that are pure process based. And hopefully you will see some examples in the rest of the talk that will touch each of these topics. So to be sort of more connected to what we are for the talk today, I'm just giving you a caricature here on the left side of the screen of an environmental system, which could be a geophysical system, which you see in the middle in a circle, which you're trying to model, which you're trying to understand. And this system is sort of impacted by physical drivers like weather, temperature, precipitation, etc. You may be interested in the response of this environmental system, which could be, if it's a hydrological basin, you may be interested in a river flow, stream flow. If it's a lake aquatic system, you may be interested in the temperature of the lake profile, lake temperature profile. If it's a farm that you're trying to grow food on, you may be interested in how much greenhouse gas emission is coming in from the farm, or how much pollution it's causing in terms of the fertilizers, or how much yield is there from this farm for a certain crop. Now, this environmental system has a response which is driven by the physical driver, but the relationship between these is determined by the inherent system characteristics, like what is the land cover, what may be the soil characteristics, how are you managing the land, especially if you're growing food, you're trying to figure how are you managing the land in terms of, are you tilling it, not tilling it, you're putting cover crops, all sorts of things can determine the response. Now, a typical goal in the physical sciences is environmental sciences is to model the response as a function of the physical driver and the system characteristics, while some of the behavior of the system may be available through external observations like the satellites, or maybe even in situ sensors. And people build physical models that are that makes use of the underlying physics to predict the response. As I'm going to mention again in a little bit, that these models have inherent simplifications into them, which makes them very hard to provide a very good quality response. And of course, there's interest in using machine learning to be able to replace those forward models. But there are situations in which, instead of trying to figure out the response, you're trying to figure out the inherent characteristics of the system. And that process is called inverse modeling, in which you're giving the physical drivers and the response, and you're trying to figure out what may be the underlying characteristics that are determining the relationship. And machine learning has has already been used quite a bit for forward modeling. Machine learning is increasingly becoming used for inverse modeling. And as you will see in the KGML framework, we are trying to bring scientific knowledge into both of these frameworks, and in some cases, doing them jointly to solve some interesting problems. And now this will sort of tell you as to what this slide tells you a little bit more about what are the limitations of the process-based model that we are trying to address using the KGML framework. So first one, of course, is, as I mentioned, that the physical models are never perfect. They're always incomplete or approximations. And to give you an example of that, let's say if I'm trying to model the hydrology of a river basin, one of the things I have to do is model the soil. And one simple way would be to sort of say the soil has certain characteristics. I model soil as a single layer, a single column of layer. But if I want to be more accurate, I have to realize that soil can have multiple layers, and each different layer of the soil can have different characteristics. Now, as I increase more and more layers in the soil, my model becomes more complex and needs more parameters. But if I simplify the model and assume it's only one layer, then I am making approximations, and my model may be inherently incapable of realizing certain reality. So, but if I have multiple layers, I have too many parameters that have to be calibrated. So basically, there is this inherent trade-off about how can I make, if I simplify the model, it's going to be naturally not very good in quality. And if I make it more complex, I have lots of parameters, and I will not know how. Then I will need a lot of data to be able to calibrate them. The other major problem of these process-based models is that even if I have a lot of data to calibrate a model in a certain location, I cannot use that calibration to a different location. As I go to a different location, then I have to restart the process. I have to collect observations and then do recalibration. So basically, the traditional process models make a very inefficient use of observations. Calibration in a highly observed region does not help improve performance on a less observed region. Now, the machine learning algorithms inherently are very good in collecting data and then using it from wherever they come. So machine learning algorithm can address this last inefficiency very, very easily. And the KGML connected with it can also then bring in the ability to make predictions with very few observations and generalize to unseen scenarios and produce physically inconsistent results. So basically, this machine learning combined with scientific knowledge has a very good potential to address all of these limitations. Now, in the remaining part of the talk, I'm just going to give you a rapid fire examples of a whole bunch of environmental systems where this methodology has been applied with great success. And again, a lot of this work is in collaboration with mission-driven agencies like USGS and NOAA and research funded by multiple agencies, as Loken mentioned earlier. So this example that I'm talking about is about being able to model the temperature profile of lakes. And why is it important? Because temperature is a master variable, and the master variable determines the quality of water, whether it's fit for recreation and so forth. So USGS, which is the mission-driven agency, is responsible for monitoring the 185,000 lakes in the country, in the US. And this is one of them. This Lake Mendota that I'm showing on the screen is one of them. And it turns out that this lake happens to be highly observed, one of the few lakes in the world that's highly observed. And what this slide is showing you on the left side is if I take a physical model, which is GLM, and if I use it to make prediction of the lake temperature by calibrating the data and how much data is being used for calibration is shown on the x-axis, and the vertical dimension tells you what is the quality of the model, that is what is the test error. And as you go up the screen, as you go up the y dimension, the error goes down. So you can see that this process-based model, which is the operational model used by USGS, has high error of 3 degrees if it has very little data for calibration. And as you increase the data, the error actually goes down to about 1.5. Now, the next slide sort of shows you that if you have plain machine learning algorithm, which is black box machine learning algorithm, and if you give it lots of data, and actually it can outperform the traditional physics guided model for a large amount of data. Of course, if you have less data, as you would expect, it does quite poorly. So but so even though machine learning is performing very well on this lake, given the amount of data we have, it's not very helpful because of the 180,000 lakes that we have in the US. There are only maybe less than a dozen lakes for which we have this kind of data. There are a few hundred lakes for which we have maybe 50 days or more data. And there are only about 12,000 lakes for which we have some data, one or some little or more data, and for the rest of them we have no data whatsoever. So this is clearly the black box machine learning algorithm is not very useful. But if you combine the power of both of them, the machine learning and the knowledge guided machine learning together, you can see that they actually outperform both of these other paradigms, even with very, very small amount of data. The next slide sort of shows you that actually this KGML paradigm is very good in going into scenarios that have never been seen before. So I'm showing you two different scenarios here with two different tables or the graphs. The left table is sort of saying that what if 500 labels were available to each of these three paradigms, how would they perform? And again, that's the number that you see on the left chart is coming directly from the previous slide. On the right part of this, the right graph on this one is showing you what happens if you hide the summer observations from all three paradigms. That is, the physical models doesn't get to see summer data for calibration. The plain machine learning model doesn't have access to summer observations. So it does both of them do poorly, but the machine learning model, plain machine learning model does extremely poorly because summer behavior is very different. But if you look at the KGML method, the physics guided machine learning method, it actually does dramatically better than both of these because it's able to learn the high level physics from the process guided model and is able to leverage the whatever data it has, even outside of summer, and learn the overall behavior. And this story, even though I'm showing you from lake temperature modeling, it repeats in many, many different examples. So this is sort of one example of being able to work with very sparse data and also being able to generalize to scenarios never seen before. This example is simply illustrating that yes, the energy conservation can be achieved in a machine learning framework if it's coded properly. Next slide is sort of giving you sort of another thread in this KGML framework, which I sort of alluded to earlier in terms of the limitation of physics-guided model or the process-guided model. That is, if they are very good, if the model is complex enough and if it has lots of data, it can be calibrated to perform quite well. But the calibration doesn't serve further entities. So this phenomenon is being sort of shown here in the form of there are multiple entities. Let's say there are n entities for which we have a lot of data. We have a certain amount of data. We have the possibility of training our models, machine learning models or physical models on these entities during the training period. There are situations in which we are trying to extrapolate the behavior of these entities into the future, which is called extrapolation in time. And there are situations in which we are trying to extrapolate in both space and time. That is, you're trying to look for entities that have never been used in training. And when I talk about entities, these entities could be lakes. There are 180,000 lakes in the US. There could be basins, river basins. There are, at a certain level of detail, there are almost 650 catchments in the United States that are captured in a global data set called, a benchmark data set called CAMELS. And then, as another example, I'm going to show you, there could be flux towers all over the world trying to monitor the greenhouse gas flux. And the idea is that there are locations, there are entities for which we have a lot of data that would sort of correspond to the green box here. But the question is, can you do the prediction either as extrapolation in time, but even more urgently, extrapolation in space and time. That is, you're going to entirely different entities that have never been used before. And this is the job that is very hard for the traditional process-based models to perform. But the KGML method, the knowledge-guided machine learning method, does a fantastic job in being able to do it, oftentimes with joint modeling of the forward and inverse model being used in the KGML framework that you can generalize very, very well. And I'm just going to give you some actual results that are operational. This is a result of 180,000 lakes that USGS is responsible for on a global scale. I mentioned to you that observations exist only for 12,000 lakes. And this methodology that I briefly mentioned on the previous slide has been used to create surface temperature profile for all of the 185,000 lakes in the entire country. And of course, this methodology was validated on the 12,000 lakes that for which observations are available. And as a result, we were able to create this unique data product that is available now to the ecological community, again, because of this KGML framework. This next slide is sort of showing the same thing about being able to monitor global carbon fluxes. And the idea here is that wherever you have flux towers, you can monitor the greenhouse gas emissions very accurately. But there are a lot of places in the world that you don't have any greenhouse gas, you don't have any flux towers. They're very expensive to emulate. And then the question is, could we build models in locations where we have flux towers, where we have a lot of data, and then take that information to other places in the world where we have no data, and then still do a good job, reasonably good job. And this slide is sort of saying that this, if you use the standard machine learning framework, it doesn't do as well. And if you do this KGML framework, which is what is the last line in this row table, TAMRL, task-aware modulation learning, and it does a very, very good job, even with very little data, and can lead to very high quality results. The last slide is sort of showing you some of the work that we have done recently in collaboration with NOAA, in which you are trying to make forecast, hydrological forecast, many days in advance. And in this graphic on the lower left is showing you that at 0 is the time that you're trying to make a forecast. As of now, you're looking 7 days into the future, making forecasts every 6 years. The star values are true observations. Of course, this is looking backwards, as pretending as if we are operating this in a real-time mode, but it's really looking at the past data. And you can see these different colors: red line and yellow line and the blue line. And the red and yellow line represent the state-of-the-art machine learning approaches, which actually do quite well relative to the physical model. But then if you have the blue line, which is sort of doing a dramatic job, you sort of see that you're looking at making predictions on 0 day, and you're making accurate predictions going as far back as 6 to 7 days. Like you're looking at literally 6 days ahead, and you're making almost accurate prediction as to how the water level is going to drop in the river. So again, this is an example of the power of machine learning framework augmented with scientific knowledge. Just want to mention very briefly that same paradigm is being used in a new AI institute that we have at the University of Minnesota, funded by NSF and USDA, to turn around to make agriculture, which is currently a heavy producer of carbon dioxide, a contributor to the greenhouse gas emission. By changing practices, our goal is to turn it into a net negative or net zero from the agriculture perspective. And the idea is that agriculture, if it's managed appropriately, it could produce a lot less greenhouse gas emission, or it may even be able to put some of that into the soil. And then, of course, to be able to do that, you'd have to be able to monitor the greenhouse gas emission. And the traditional process-based models, again, for all the reasons I mentioned to you earlier, are extremely poor in being able to do the right kind of predictions. And this slide is sort of telling you that if the dots happen to be the observations, the green and blue line happen to be the physical model and the pure machine learning model, and the red line happens to be the one that's the KGML model, which learns largely from the imperfect physical model, but makes efficient use of the observations to be able to make very, very good prediction. The next few slides sort of give you some other examples. This is sort of saying how the deforestation is happening, how do you monitor it effectively to be able to incentivize countries not to deforest their land and protect them for future. This is sort of talking about being able to build a data set for the entire globe of freshwater bodies, so that people can figure out how they're changing and how they're being impacted by human actions and climate change. And this slide is sort of representing a whole bunch of other different projects we're involved in, being able to understand the climate teleconnections, being able to figure out what crops are being grown at what locations. In this case, you're seeing the picture for a region in California, and you're seeing that the two pictures for the crop map, left one is being produced by USDA, and the right one is using methodologies that I just talked about, and you can see the dramatic improvements there. So with that, I think I'm running out of time. So I just want to sort of just again, mention a couple more things here. This is a workshop that we organized at NSF last year. And again, the whole idea of this workshop was that so far, much of the advances in machine learning have been driven by just two domains, computer vision and language modeling. And those advances have been phenomenal. They have changed many things in our life. But the idea of this workshop was that perhaps there's a possibility to have the advances in AI driven by the needs of the scientific problems, which could eventually then revolutionize AI and of course dramatically improve the ability to solve some of these major problems. And KGML, of course, is one of those methodologies that would sort of come out of this. So to conclude, just to finish in time, I'd like to summarize that big data and machine learning offer great opportunities to increase the understanding of the Earth's climate and environment, but addressing challenges that are unique to these problems require entirely new methods in machine learning, and KGML is an example of that. And the methods that incorporate scientific knowledge into black box machine learning approaches have applicability across a very diverse domain. They're literally being used in every application that you can imagine. With that, I'd like to thank the audience and acknowledge my agency that have funded this research and the team members as well as the collaborators I have around the world. Thank you. I'm happy to take any questions.
All right, thank you very much, Dr. Kumar. Excellent talk. Any questions out there from our attendees? If you have questions, you can type those directly into the questions window. Also, there's the option to raise your hand, and you can ask a question via voice as well. I'm able to unmute you if you want to just ask a question directly. So any questions out there from the audience?
I do have a few questions, but I guess let's go through the audience questions first and then I'll get to it.
Somehow I'm not able to see the audience questions, so if you could just read them to me, that'll be great.
Yeah, we're still waiting on audience questions. I'm not.
Oh, okay, all right.
Okay, so maybe I'll start with a few questions. Let's say,
yeah.
Did somebody say something?
Go ahead and ask your question, Lakendra. Yeah.
Oh, okay, yeah, sure. So, so you talked about KGML and how it can work with low amounts of data and so on. But like, what is the risk of like finding some spurious patterns, or basically likelihood of finding spurious patterns in terms of when we are trying to generalize, or what? How do we do uncertainty quantification better in these cases? Like, do you do those also?
Great question. So let's take them one by one. Any machine learning algorithm is meant to be finding statistical relationships in the data. So there's always a risk of spurious relationships. Remember, we are only finding relationship, not causality.
Yes.
What KGML does is it reduces the possibility dramatically. Okay? By being able to bring in the physical laws, it sort of makes it much more likely that the relationship would be generalizable in space and time. And some of the examples I showed you were concrete examples on regional scale, national scale, even global scale. The Flux Tower was on a global scale to show that indeed you can have much better performance for generalizability as you go out of sample scenario. So again, extremely important point. One should never trust a machine learning algorithm to go out of sample unless you've tested it. And some of the biggest failures that we have seen of machine learning, biggest disappointment, have been because of out of sample scenario. I mentioned very briefly on a slide the Google flu trend. That's exactly what happened to it. In 2012, Google built a model to predict outbreak of flu just by looking at the queries that people were typing on Google search. And it turned out the model did extremely well. In the year it was built, it was able to predict the outbreak of flu 2 weeks before CDC would predict. But soon after, a couple of years later, the model sort of went out of whack and started, over predicting, and making some random predictions. So basically, it just is not generalized. The queries, the connection between queries and outbreak, which existed in 1 year, did not carry over to the next year. Okay? So this is a big risk, but by being able to generalize these models, by being able to incorporate the scientific knowledge into the model, you bring in the flavor of generalizability, which is much more robust than you can have otherwise. So that's the point number one. That's an extremely important one. That's one of the biggest advantage of KGML. And again, that doesn't make KGML proof in the sense that it doesn't mean that it'll never, it'll always be able to generalize, but it gives you a methodology for improving the generalizability. It gives you different ways of making sure that you can generalize out of sample scenarios. And when I mentioned to you in one of the earlier slides about these entities that are, you're sort of going through, the extrapolation in space and time, this is exactly where the KGML really shines. Okay. Now, the second point that you mentioned is extremely important, which is being able to quantify the uncertainty. Now, it turns out that much of the focus of the machine learning community so far has been on predictive performance and a lot less on the uncertainty quantification. And uncertainty quantification is an extremely important topic of consideration in physical science community. If you're building a model, if you're making prediction, you always want to be able to know exactly how certain or uncertain you are. And now our community is increasingly paying attention to this and bringing in basically building framework in the machine learning community to quantify uncertainty. And one of those frameworks is actually the variational framework. So I didn't talk about those results here, but we are finding the incorporation of variational framework inside the KGML models allows us to give much better ways of uh, of quantifying uncertainty and actually figuring out much more information than you would get otherwise. So uncertainty quantification is an important topic, but it's beginning to be incorporated in KGML.
Okay.
Thanks for
Do we
that.
have any other questions? I have some.
Yeah, we do have a question from the audience. Vikash Kodati, I see you have a question. Just sent you an unmute request. So I think you can unmute now if you just want to ask your question directly, Vikash. Yep, you are unmuted. Go ahead and ask when you're ready. We should be able to hear you, hopefully. Can't hear you right now.
I see. Lost him. Okay.
I can see him online, but we can't hear your.
Okay.
Can you hear
I
me?
can ask another one. I already.
Are you able to hear me?
Yes, we can hear you now.
Yes, we can hear you now. So sorry, logistical problems. Thanks for the great session today, very informative. I was curious to know how one can apply these learnings in the domain of space, particularly in the data that is available in the Earth observation industry, or the other way of calling it, the geospatial intelligence.
Oh, actually, many examples. Okay, I guess there's a. So the last three examples I showed you were all about geospatial data. This is geospatial data purely from satellite, no physical models, and you're trying to build the spread of these oil palm plantation. And this became a very important problem because once people figured out about 7-8 years ago that oil palm plantation is actually not very good for the environment, many organizations around the world promised not to source any product from recently deforested land. For example, places like Cargill, General Mills, some of these biggest corporations. So non-profit organizations sort of came up to build these models, build these maps by hand. So RSPO created a map for 2005, 2009, which are very limited map in the sense they're not very complete. The Transparent World, another organization, we created a map in 2014, about 10 years ago, with manual annotation, and it's highly inaccurate. So they were very painfully created and either incomplete or inaccurate. Now, this methodology, KGML methodology that was built, was able to basically create these maps year by year, as you can sort of see on the screen, starting in 2000, exactly how these plantations are growing, and was able to verify, of course, with very high resolution imagery, through validation. And again, that's how this work sort of received community acceptance. When I mentioned to you about this water bodies, it's entirely, actually, I would say the KGML framework grew out of our initial work on being able to do this mapping. And now we are using the same methodology to map the lakes on the polar regions, which are extremely sensitive. As the earth is warming, the snow is melting on the polar regions, and it's creating lakes. And as the water becomes exposed, it sort of starts emitting methane, which is highly potent gas from greenhouse gas perspective. And there's a lot of uncertainty. And we're using these methodologies now to figure out the dynamics of these lakes in the polar regions, which are going to inform the greenhouse gas emission. And again, if you look at these, being able to map crops at finer and finer scale, it's all geospatial data, no physical models here. And again, KGML methodologies, variations of the ones that I just talked about earlier, are being applied here. Like inverse modeling, basically you use combination of forward inverse modeling in this context to build better maps of crops and better ways of understanding the greenhouse gas emission and so forth.
So that's very helpful, Professor. A follow-up question on that is, as you said, there is that Earth observation data, a bunch of satellite imagery that is already available. And there are algorithms that convert that data into other data structures on the Earth. Now, you can please say that one more time. How does KGML help with in the process that you just outlined? You got the data imagery. Where does the KGML help?
Oh, okay, all right. So I'll since I'm on this slide, I'll just tell you. For example, if I'm trying to map the crops, the traditional method has been to take the spectral signatures and use them to classify the land pixels. CDL, the crop data layer that the USDA produces every year, it uses a series of algorithms to basically provide you a map at the end of each year. And it's driven by the satellite data. It happens to use Landsat data and series of algorithms. Now, on the map on the right side that you're seeing being produced is actually treating this problem as an inverse problem, that you're sort of saying there's a weather that's driving the crop production, and it's being watched from the sky using the spectral signatures, and the how the crop appears to the satellite is actually determined by both the weather and what crop is being planted. So by modeling it as an inverse model process and then building a machine learning framework, it's actually become a very powerful framework, and you can do a much better job. So the information about the underlying process can be incorporated in the ML framework in many levels. So there are papers that we have published. Actually, this paper on inverse modeling based approach to crop mapping was just published about a month ago. So these are all different ways in which you're bringing in the understanding of the physical processes into the machine learning framework to make it better.
Got it. That's very informative.
Do you want to add that the carbon measurement example from your recent work, where you guys, I think, took the principle of conservation
exactly.
of carbon?
And the carbon example is just sitting at the bottom, which is, let me bring it here. But this example is a physical model learning. I thought the question was, if I'm completely in the geophysical domain, there's no physical model, how does KGML help? But if you have a physical model, which is what we have in this case of greenhouse gas sequestration, then of course it's basically the model. The KGML model here is working almost the same way as it is working for the hydrology or for lake temperature modeling, which means there's a physical model which has an understanding of how the input-output relationship is governed by the physics, but it's not perfect. But there are some observations, and the KGML model is basically leveraging both the observations and the process-based simulation and the structure to build a more robust model.
Sure.
Yeah, so I covered a whole bunch of examples in this talk. Some of them assume ability to have the underlying physics model, which is all the way up to here. And all of the examples I show you after this assume that there's no physical model and just observations, and you're trying to improve the modeling by having a better understanding of the physical phenomena. and applies to this slide, applies to this one, in which you're trying to map the water on the surface of the earth, how it's changing. And if you use a classification algorithm that uses spectral signatures to make classification, they can be very good, but they always make mistakes, which means you will always have false positives and false negatives. But then if you bring in the physical nature of these water bodies, that they can grow and shrink in a very logical way. They cannot be arbitrarily fractured, from time to time. And by incorporating that information into the machine learning framework, you can create very robust global maps, even using classification algorithms that are inherently buggy to begin with. So this is an example of how, in a pure data-driven framework, understanding of the physical phenomena makes your entire framework much, much more robust.
Okay, thanks.
And again,
also
same thing
makes it more
happens.
explainable,
Yeah,
I
and
guess,
same thing
in
happens
the-
with the crop mapping thing. Yeah.
So we do have another question from our
Okay.
audience here. The question from Malika Sadati is, when infusing domain knowledge into deep learning architectures, there seems to be a choice between integrating it into just one layer or spreading it across multiple layers as ResNets do. Could you elaborate on the pros and cons of each approach? For instance, infusing knowledge into one layer might simplify the model and reduce computational complexity, but it might also limit the depth of integration and the model's ability to learn complex relationships.
Absolutely, absolutely. Very good observation. And already on the right side of the slide, you can see multiple ways of incorporating knowledge. And the first one is the easiest one to incorporate knowledge in which you keep the machine learning framework and you simply modify it by adding a loss function that relates to the scientific knowledge. For example, in some of our previous work, we have kept track of the energy gain and energy loss. And as you sort of match them, you can sort of check. As you try to modify the parameters of your machine learning model, you not only penalize because of the difference between the prediction and the observation, but you also penalize if there's a loss, if you're not matching, if you're not following the physical laws. Right. So this is one of the simplest ways of modifying a traditional machine learning algorithm. That is by incorporating logic guide loss function. The second equally simple way is to use the data. We call it free data because it's the data that's free, synthetic data from the scientific model that you can use it to generalize, to initialize. And if you do that, the models become more robust and more easy to reach a final value even by small number of observations. So the idea is, if you had a lot of observations, of course you will get to the right structure. But if you initialize the model even using imperfect data, then it takes only a small number of observations to get where you want to get to. You saw the example in the case of lake temperature modeling that even with 2 observations, 2 days worth of observations, but pre-training the machine learning model using imperfect scientific model, you can actually get very, very good results. So first 2 are extremely easy, requires no understanding of the very little understanding of the underlying process model. The third one is far more complex. Here you're looking at innards of your process structure and trying to bring that inside the machine learning framework. And it's a series of ways you can sort of do that. And again, as you get more and more, as you explore more complex ways of designing architecture, you can bring in more and more kind of knowledge into the machine learning framework, but then it's harder to do as well. You cannot do it easily. And of course, hybrid KGML model becomes even more involved. So this sort of gives you a sense of what is involved in building these models. But the first 2 bullets that you see on the slide are some of the easiest ones. And those are the ones that are being used extremely widely by everybody because they're so easy to use. But if you need more performance, you have to go deeper and go into the 3rd bullet and perhaps even into the 4th bullet.
So I have one final short question. I don't know.
Okay.
So I guess we talked about agriculture and other climate-related problems. So that's mapping and all. So that's there. But for geospatial industry, another big segment is that relates to urban computing. So whether we're talking about being able to make building level spatiotemporal predictions about, I don't know, let's say air quality or pollen, or even trying to crowdsource data and then make predictions using, and crowdsourced data is inherently very noisy. So So are there any specific ways in which we can use KGML there, or have you worked on any of it?
Absolutely. I mean, literally, as I mentioned to you on the last slide, literally every single domain is using KGML now, sometimes using different names, but the overall idea is being used everywhere. I mean, and you say urban computing, you mentioned transportation, of course, tremendous possibilities. But as we move to the zero carbon economy, we are, and using renewable fuel, we'll have to do a better job of predicting the energy needs and energy availability, And again, same limitations apply. You're trying to model these big buildings. If you build a very precise model, then you need too many parameters. You cannot take the model from one building to the other. If you have too few parameters, you simplify the building, but then you cannot carry it over. Then you have inherent biases. And again, the idea of entity, being able to generalize across space and time works perfectly there. So the idea that I'm talking about here, even though we have tried them in our own group in the context of hydrology and aquatic sciences and in agriculture, but they're applying everywhere. I mean, we're beginning to apply them to design of new materials, for example. Now, people are applying it in neuroscience. People are applying it in epidemiology. And the book that I mentioned earlier that actually has examples from many of these areas in it being applied. Where you have used KGML to apply to these domains.
Okay, great. Thank you so much.
And great timing. We're right at our cutoff time now. Thanks so much, everybody. Really appreciate your presentation, Dr. Kumar. It was excellent. Really great conversation and questions there. We will have another session of the OGC GeoAI Speaker Series in about a month. So expect to see details being sent on that shortly. And I will follow up also with a link to the recording. We will put it up on YouTube and also on our GeoAI Domain Working Group landing page. Thanks again. Really appreciate everybody's time today. Let's give another round of applause to our distinguished speaker. There we go, virtual round of applause. Thank you again, Dr. Kumar. And we hope to see you at our next GeoAI Speaker Series session. Thanks so much, everybody, and have a great day.
Yeah, thank you. Thank you. Bye-bye. Take care.